We are going to present our topic on application of third order plate theory to the analytic solution of clamped rectangular plate. This presentation is done by Onyeka Festus Chukwudi from the Department of Civil Engineering, Edo University Iyamho, Nigeria, and Okeke Edozie from the Department of Civil Engineering, University of Nigeria Nsukka. Our contact address is 0+234 806 82 85 789. Introduction. The importance of plate structures in aeronautic, automotive, military, and structural engineering cannot be overemphasized. With increase in the isotropic plate material, the need for an improved approach for stress analysis is easily discovered. So in structural engineering, it is applied in plate is applied in ship hulls, the retaining walls, brick deck, even in a slab in a building for more adequate reinforcement. So in such material, transverse shear stress and strain, which induced by the applied load, affect the bending characteristics of the plate structure. So we analyze the bending due to the applied load stresses, which efficiently causes the plate structure to be unstable as per equilibrium. So we analyze to balance the equilibrium and avoid the instability of the structure, so that the structure can resist the load of this member. Because the structural failure and incessant collapse of the buildings, bridges, and all these structural elements is because of inability to predict the stresses in their member. So in a thin plate model, which is generated by Kickoff, we discovered that Kickoff developed thin plate model in a classical displacement theory, in classical plate theory, and in their theory they underestimate the effect of shear deformation. But Zekon, in his work 2003, discovered that the stresses in the members cannot be underestimated when the plate is thick. So the thick, in the trigonometric and hyperbolic function, one can startly see work based on plate theory using the polynomial displacement function. The rationale of this work is that the previous studies have used classical plate theories which cannot be applied in the thick plate analysis. So avoid structure, and when you are using classical displacement method, the classical plate theory, find out that the structure might not be safe and lead to failure, structural failure. So to avoid structural failure and the building collapse, which is attributed to inability of the designer to estimate the load and the stresses in the structure, can lead to structural failure. So to avoid psychological trauma and thought of not too sure of the other tedious methods of structural analysis, the method of direct variational calculus is the way out. The study objective: to formulate potential energy of a thick rectangular plate. The second one is to obtain the solution of resulting three simultaneous governing equations. The third one is to obtain the formula to calculate coefficients of deflection and shear deformation along the x and y axis. The third one is to determine the equation for displacement, stresses, and stress resultants. The stress resultants of the moment, bending moment. The stresses here includes the normal stresses along the x and y axis, the shear stresses for x, y, z and the y, z, z axis. So the literature here is that the theory is due to the classical theory that was organized by Kirchhoff it neglect the effect of transverse shear deformation, and that means the proposed theory which we are using to analyze here, called refined plate theory, is a proposed, and in the previous studies people have used first order and second order. The first order shear deformation theory use shear correction factor to consider the effect of shear deformation, which is by Reisner and Medley. And also we have second order, third order, who people have done work like Kramers, Krishna and Toratia in 1991, 2013 for Sahat. Pagna also used a hyperbolic. So, but you see that these people have used, like Krishna used exponential, and this use hyperbolic, Pagna. And then we have Sayat also use a trigonometry function for the analysis. But in this work, the higher order shear deformation theory using polynomial function to study the bending behavior of a thick rectangular plate carrying uniformly distributed load is going to analyze. So the research methodology is based on a thick plate like this, where we have the long span being B, and then short style which will have a design load to be A, and then here is the middle surface of the plate. From here to here is T divided by 2, but from here to here is the thickness of the plate. Z is the Z axis, Y along this axis is Y axis. The horizontal axis, of course, is the S axis. We are considering the case of a plate climb at both edge, so that is our method. So we are going to use energy method by formulating the potential energy expression from the elastic static theory. So when we do that, we find out that the U is the pi is the total potential energy function, while U is the strain energy, V is the work done. So we have pi to be equals to U plus V. So formulate our equations to expression of strain energy. We know that our Q is the uniformly distributed load, while W is the deflection along the S and Y axis. So also for strain energy to be formulated, you know that it's a product of the stresses in the members, So what we are going to do here is that we did the direct variation we formulated the direct variation to the potential energy equation by differentiating the total potential energy formulated with respect to the coefficients of deflection and shear deformation rotation along the S and Y axis. So when we do that, we put the equation in matrix form, and then we solve. When we solve the matrix, we find out that the A1 being the coefficients of deflection is formulated in this equation using the polynomial shape function as derived from the governing equation. We got the shape function H to be equals to R square minus 2R cube plus R4 times QR. This R and Q are the R, of course, is the non-dimensional value of X, while the Q is non-dimensional value of Y. Displacement and stress resultants formulation. So in the analysis, having known that the deflection is a product of the shape function and the coefficients of deflection, when we haven't gotten the value for the shape function, we put that equation into the already established coefficients of deflection, and we'll get our deflection equation. And then for this is of course we have to do that to get we drive our expression, and we got the expression for the in-plane displacement along x-axis, which is u. We got that of y-axis, which is v. We got our values for the moment along x-axis, the value of moment along y-axis, and shear force qs along x-axis, and qy, which is shear force along y-axis. Of course, when we do that, we now find we have stress along the x-axis for the normal stress to be equation 15. Stress along the y-axis for the normal stress is equation 16. Then we have the shear stress along the x and y-axis to be equation 17. Equation 18 is the shear stress along z-axis. Equation 19 is shear stress along yz-axis. So when we got all these equations, we now discover that all these equations are closed form solution, because in our deflection equation we did not assume the value of displacement function in function of polynomial. Rather we derive it from the governing equation, and then we got exact displacement function, exact displacement polynomial function. So using variational calculus, we got the values for the coefficients of deflection and shear deformation. In our analysis, we use the statistic elastic theory to derive the formula for stresses and strain, putting the value of the coefficients into the expression, and then we're able to find the developed equation for the stresses, which we have in equation 15 to 19. Using the result of the equations, having known that W is the deflection, U is the in-plane displacement along y-axis, YV is in-plane displacement along U is the in-plane displacement along x-axis, YV is in-plane displacement along y-axis. Then moment along xy axis ms, my is moment along y axis, qs is shear force along x axis, but qy is shear force along y axis. So we have the stresses, the normal stresses along x axis and y axis. So these are the shear stresses. So when we got these values, generated our numerical values. These numerical values are not dimensionals. They are non-dimensional. So of course we now find out that as we are increasing the thickness of the ratio of the thickness to the ratio of the span to thickness, we find out that our deflection, our shear, the whole displacement, that is the out of plane displacement and the two in plane displacement, are increasing. So until we get to a point where they're almost at the equal to the value of CPT, the value of classical plate theory. So at the value of in-plane displacement 80, find that its value are equal to the classical displacement theory, of which is CP result is 0.0133. So the same thing with the shear force and bending moment. When we come to the stresses, you'll find that that our value is even constant, even as at 30, even as at span thickness ratio of 30. So when we look at this value is actually for the square plate. we did this work in two values, all right, in the sense that we did our simulations for the square for the ratio of length and width being 2. We also get our values for the deflection, the whole displacement and stresses in the members from that 4 to 100, and we compare the value with the CPT. We now find that the value as at 30 is almost equal to the value of CPT, you know. And then we have the shear stresses here. We find out that from overall value, we find out that the increment we have as the span to thickness increases, all right, the value of these quantities decreases, all right. But at the same time, when the value of length, ratio of length to width, you know, increases, the value of this quantity increases also. So to infer in our discussion, because in our discussion we discovered that the results of the in-plane displacement, the out-of-plane displacement W, and the stresses increases as the ratio of length to breadth increases. But the results show that the value of moment and the shear forces increases as the span depth thickness increases, while the value of these quantities, the displacement and the stresses, decreases as the span to thickness increases. And this becomes insignificant from the span ratio of 15. So when we look at those things, we now find that the value of these quantities from all the span thickness ratio are close relative, but vary with classical plate theory. So the value of the span thickness ratio of 15 and above are equal to the value from CPT. So this shows the boundary that from the value of from the span to thickness ratio of 15 and below, from the 4 to 15 can be called thick plate, but anything from 15 downward can be referred as a thin plate. That is one of the discovery of the. And then in the conclusion, we find out a displacement-based refined shear deformation theory, which includes the effect of shear deformation in my work. So in my work, I include the effects of the shear deformation. But this effect of shear deformation satisfy the constituent relation in respect to in-plane stress and transverse shear stress. So this theory obviates the need for shear correction factor. The shear correction factor is actually associated with thin plate, with lower order shear deformation theory like first order and second order shear deformation theory. So by adding the complication to take care of the effect of transverse shear stress. So the value of stresses obtained by this theory is, of course, achieve acceptable vertical shear stress to obtain thickness or the plate variation, and this satisfy the transverse flexibility of condition at top to bottom faces of the plate, while predicting the flexural characteristics of a plate with this